All right, so in the last video, we looked at a matrix that was diagonalizable, and we talked about how to find that matrix raised to any power. We can use its diagonalization and just raise the diagonal matrix that it's similar to that power. So let's actually do this example, a cubed, with these matrices here. All right, so a cubed is going to be p d cubed P inverse. All right, so using these matrices here, we have our P, our D cubed. So remember that's going to be 2 cubed, 0, 0, negative 1 cubed. And then we need P inverse. Luckily this is a 2 by 2, right? So we're going to do 1 over the determinant. So 2 minus 1 should be 1. Then we're going to switch the corners, make the other corners negative. All right, so then we will work through this multiplication. So I'll do these two first. Feel free to work this on your own and pause the video. I'm just going to jump straight to the answers here. 8, 8, negative 1, negative 2. And then we have this matrix here. The inverse of P. All right, and so when I multiply these two together, I get the matrix 17 down the columns, 18, negative 9, negative 10. All right, so this took about as much work as it would have taken to multiply a 3 times. But you can imagine when this number gets bigger, like a to the 100th, this method may be a bit easier, or at least easier computationally if you wanted to use a computer. Okay, but how do we even know if a matrix A is going to be diagonalizable, and how would we find the diagonalization? That's what we're going to talk about next. All right, so let me write down this question for us. Question: how can we find a matrix's diagonalization if it exists? All right, because it may not even exist. We may not even be able to diagonalize it. So if A were diagonalizable, we would have that A equals P D P inverse. Be very familiar with this. You'll use it a lot. Okay, this is kind of difficult to think about conceptually. So what I'm going to do is multiply by P on the right side, on each side of my equal sign. So I'm multiplying by P on the right side, so I get AP equals PD, and then we'll have the identity. So AP equals PD. All right, let's talk about what each of these matrices look like. So let's start with the P. All right, P is just some n by n matrix. So we know we can write it as just, column vectors side by side, right? V1, V2, all the way to Vn. That's our matrix P. And then we have our matrix D, which we know is a diagonal matrix, so it only has numbers in the diagonal. And I'm going to be very strategic about how I write it. I'm going to call the diagonal elements lambda 1, lambda 2, all the way down to lambda n, and we got zeros everywhere else. So you may see where we're going with this example. All right, but in general, this is just a matrix P. This is just some diagonal matrix D. All right, so let's think about what this means when we multiply. So if you multiply A times P, we'll get another matrix. We could write it as A times V1, A times V2, all the way to A times Vn, right? These are all column vectors side by side to make a matrix, which means that PD, these two multiplied by each other, we can do the same thing, but these are just going to be numbers, right? So we can do lambda 1 V1, lambda 2 V2, all the way to lambda n Vn. So that means that AV1 should equal lambda 1 V1. AVN should equal lambda n Vn. So what does that tell us? For any position, we could say that AVJ is going to equal lambda j Vj. And this should look very familiar to you, right? This is the definition of something we've learned before. It's the definition of an eigenvector. All right, so the question was, how do we find a matrix's diagonalization if it exists? Well, if we have these, which are our eigenvectors, right? And these, which are, so these are eigenvectors of A, and these, which are our eigenvalues corresponding to those, if we have the right number of these, then we can diagonalize A. So that's actually going to be the answer to our question, and I'll write it out. So the answer, we need n linearly independent eigenvectors. So if our matrix A has n, so the same number of columns and vectors, n linearly independent eigenvectors, then it's going to be diagonalizable, where we can break it up into P, D, P inverse, where P is just a matrix of the eigenvectors, and D is a diagonal matrix with the eigenvalues down the diagonal. And so that brings us to our important theorem, the diagonalization theorem. All right, so note this is a named theorem, so you need to know what it says. You need to know it by name. All right, and it says an n by n matrix, so a square matrix, we'll call it A, is diagonalizable if and only if our matrix A has n linearly independent eigenvectors. All right, so our matrix A is diagonalizable if and only if it has n linearly independent vectors. All right, so here's another way to say this. So in other words, A is diagonalizable if and only if there are enough eigenvectors to form a basis in Rn. All right, so A has to have enough eigenvectors to form a basis, which means they need to be linearly independent in Rn. And we actually have a name for this basis. We call this an eigenbasis. So it's a basis made up of eigenvectors.